Hi. So in the previous lecture, we talked a little bit about pyrolysis. We started talking about it, and you learned that when you heat a polymer, and then it gets thermochemically decomposed, that is something which is known as pyrolysis. And after that, what we get? We get carbon. We also get some gaseous materials and some smaller hydrocarbons and so on. At the end, you get carbon. So we learned this technique in the context of graphite preparation. So we just learned that there is polyvinyl chloride and certain graphitizing polymers, which when they are pyrolyzed, they give you graphite. Okay. Now I'm going to tell you a little more about this method of pyrolysis, which will also take us to our next graphite preparation method. What is pyrolysis? Now you learned it only in the context of solid polymers, but can we also apply it to other organic materials? So we are going to go more into the details of this process first. So you learned that if you keep something in the furnace and you have no oxygen, and then these molecules break and then leave, that is what you know as pyrolysis. But how do you formally define it? So that was the process that you do inside a furnace. So that process you call pyrolysis. But chemically, what's the definition of pyrolysis? You can you can derive it yourself. That pyrolysis is basically the part where there is the thermochemical decomposition of your polymer. Now, it's not really the process which you perform in the furnace. You should not call that pyrolysis. It's the chemical process that is called pyrolysis. But it's like, any other process. For example, if freezing is taking place, freezing is actually happening at molecular level. But when you freeze something inside a refrigerator, you also call it freezing. So it's like, this is the process that you are performing. But at a chemical level, the definition of pyrolysis is the thermochemical decomposition of any organic material, and that must happen in the absence of oxygen. Okay, why is it so important that we don't have oxygen? To prevent burning, yes, but by definition, well, this thermochemical decomposition must be solely thermal. What does that mean? That means that there should be no other reaction such as oxidation. So whatever you're losing non-carbon atoms, but you must be losing them because of only heat treatment and nothing else. So it should be purely a thermal process, and that is why we make sure that there is no oxygen, except for whatever the polymer itself contains. Now, I have written a couple of times here that I've not written polymer, I've written any organic material. And that is something very important to us, because this process actually, yes, we use it for polymers, but this is not really limited to polymers. Any organic material. Organic materials can also be gaseous. You know that methane is also an organic material. So any organic material. In fact, pyrolysis was initially done more for the gaseous hydrocarbons rather than for the polymers. Okay, so the point is that any organic material, because it's carbon-based material, will always yield some carbon after thermochemical decomposition. After pyrolysis, doesn't matter whether it's a solid hydrocarbons are your polymers, liquid hydrocarbons. So for example, pitch, that is your liquid hydrocarbon, and any gaseous hydrocarbon, for example, methane, acetylene, you can think of many gases. All of them, whenever they are decomposed, they will always yield some fraction of carbon. The fraction may differ, but you'll always get certain amount of carbon. Okay. Now you can, of course, by tuning the pyrolysis conditions that we also learned in the previous lecture, by tuning, for example, the rate of heating, or changing the catalyst. In some cases, you'll use a catalyst, and so on. You can, by changing or tuning these parameters, or changing also the chemical properties of your precursor, now you can get different fraction of pyrolytic carbon. So what is pyrolytic carbon? Pyrolytic carbon is prepared after any organic material is thermochemically decomposed. Okay, so now we are going to talk a little more about this pyrolysis of gaseous hydrocarbons. Okay, now how do you heat a gas? Well, it's not that difficult, right? If you have a chamber and the chamber itself is heated, let's say about 1200 degrees, then the gas will heat up. But it's not as easy in the case of gases, because also even if they heat up, then what happens? Where does the carbon go? You need to make sure that you are somehow able to collect that carbon, right? So what we can indeed do is, rather than heating the entire chamber, we can have a substrate. What is a substrate? Any sort of solid surface where you can deposit something, that is known as substrate. Either deposit something or pattern something. For example, for a lot of fabrication purposes, you use silicon wafers as substrates, or you can use also quartz substrates or metal substrates, or anything where you can collect something is known as the substrate. Okay, so what we can do now, in a chamber we flow one hydrocarbon, typically with a carrier gas, because you want to also control the concentration of this hydrocarbon. So you'll have a carrier gas, and obviously the carrier gas should not be participating in the reaction, so that will be an inert gas. Also, if you want the carrier gas to somehow induce catalytic activities, then you can choose a different carrier gas, but typically you will have one hydrocarbon that flows inside your furnace. Now, if you have a heated substrate which also serves as a catalytic surface, then your hydrocarbon will only crack on top of or around that surface, and not in the entire chamber. Because if you crack the hydrocarbon, let's say in the entire tube of your furnace, then the hydrocarbon will also deposit on the entire tube of your furnace. You don't want that. You also want to be able to collect that, and also you don't want to make your tube, your entire furnace, full of carbon every time. So what you will do is you will collect this, carbon which comes from the hydrocarbons, that you will collect on a catalytic support or catalytic surface which is heated. Okay, now this process has been used for a very long time, and not just for carbon. It has also been used for silicon, some other elements, some other materials also. In fact, even compounds can be deposited by this method. This process, then a refined version of it, when it is used for not just carbon but for anything, the more general version, let's say, is known as chemical vapor deposition. So this is a term you will hear a lot whenever you do any fabrication, especially any microfabrication. You will hear the term chemical vapor deposition a lot. That basically, as the name itself suggests, there is a chemical vapor, and then there is something that is being deposited from it. So this I have drawn here. This is a schematic. What you see here, there is a heated substrate. On top of that, if you see this thin yellow line, that is your catalyst. And this is heated in most cases. Now, let's say you have a gas A inside your chamber. Now, because of the heat, purely because of pyrolysis, that gas cracks into, let's say, B plus C. Now, if you want C itself to be your final material, then you're good to go already. Now, if you want something else, you can modify your catalytic support, or you can add also with A. You can also add some other support gases or carrier gases, or then you can actually get some other you can have another chemical reaction where this catalyst or something else from the environment reacts with your material C and gives you some material D. So this is a very general form. As I said, that this can also be done for non-carbon materials, but in the case of carbon, you call this process as pyrolysis, and this kind of carbon is known as pyrolytic carbon. So the carbon that you get from your pyrolysis of a polymer or pitch, that is also called pyrolytic carbon, and this is also because pyrolysis is the fundamental process that is happening. It's the process of thermochemical decomposition of an organic molecule. Now, what is very interesting is that when you deposit the layers of carbon, what kind of carbon do you think you will get? I mean, when we were learning about quiche graphite and all, we talked about that whenever there is this atomic deposition of carbon, what you get is graphite, or you get at least graphite-like carbon. So carbon tends to make hexagonal sheets because that is the most stable form of carbon. Here also, in this case, if you have an entire film of, for example, copper, you will get some sort of carbon film, and that film, however, does not have a 3D crystal structure. So it has this random organization of sheets. And those sheets you actually also call graphene sheets. Because you know, right, that multi-layer graphene, that's the only difference. So if you have graphene sheets, they will contain a lot of defects. Their sizes may not be uniform throughout. And if you, however, control the CVD parameters to some extent, you can get, if not single, maybe bi-layer graphene. It's like, 2 layers of this entire material, because you want to make the film as thin as possible. But in that case, you may also get more defects, because you have this dendritic growth, or the film growth, right? And in some cases, then the film is not properly grown, or it has a lot of still a lot of defects, and you stop the process. So in that case, you can get thinner layers, but then the quality of the graphene may not be so good. But this is a process actually commercially used for making the graphene flakes. Also, what you can do is, if you change the catalyst, then if instead of having a catalytic film, what if you have catalytic nanoparticles? Then you can only grow your carbon structures on that nanoparticle, around that nanoparticle. Now, if you also can change the shape of your nanoparticle, like you can have them spherical, you can have any polyhedron kind of structures, because that depends on also what metal do you want to use. Typically, you would use iron. Now, if you have these nanoparticles, then what happens? Then your carbon, one layer deposits, and then the second one, and the third one, and so on, and you may end up getting tubes or fibers. Now, this is what a carbon nanotube is. So both carbon nanotubes, the vapor-grown carbon nanofibers, and as well as your graphene flakes, these are fabricated, these are synthesized using this CVD process. However, in today's lecture, we'll talk about the graphene and carbon nanotubes separately. Of course, we'll have more detailed lectures on this. Now, our goal is to make graphite. Now, right now, what do I have? I have a large sheet of copper, and I have some these graphene sheets deposited on top of that. However, they are randomly oriented, means that is called turbostratic arrangement. This random orientation of graphene flakes on top of each other. Now we have turbostratic graphene, and we want to get graphite. How do you do that? So how do you do that? You need to provide some sort of energy, some sort of heat, which will which will force your graphene sheets to now get into a more stable form, which is graphite. Okay. Now, before we talk about that, here I'll tell you a little bit of history of this kind of pyrolytic carbon preparation. So this is, it's not like it's a very new process. Often people think that, graphene is a very new material and it's advanced material, yes, you can call it. But new is not really correct, because different forms of similar materials were always there. It's just that people did not use them for technological applications. People did not think of it as a useful material, in fact, for a long time. So whatever you prepare by CVD, that was just called carbon, pyrolytic carbon. And people did not really directly use this pyrolytic carbon. Now we do that in the form of graphene. But what people did in the past is they always tried to prepare graphite out of it, because that was the goal. Graphite is like the better quality, best quality industrial carbon. Okay, so however, this pyrolysis process was very much studied and understood, and we also and scientists also tried to understand, will all organic materials give you carbon, and if yes, then what kind of carbon, and what are the conditions? So this whole optimization which led to the current day CVD of carbon materials. So how did it all start? Well, it is known that all the hydrocarbon gases will produce some sort of pyrolytic carbon, but there will also be some combustive carbon. What is combustive carbon? Which is, when you burn the any material, which means that, as I said, that there may be some oxygen always present also in the organic molecule. So there will be always some combustive carbon and some pyrolytic carbon. So now we should clearly have these two things separated in our mind, that it's not the same. Pyrolysis definitely is purely thermochemical. But if there is some oxygen, whether it is supplied from outside or whether it is from the polymer itself, there will be some combustion as well, some burning as well. So what you will get is combustive carbon. Combustive carbon is what you also get from your, car exhaust. That is combustive carbon. So you will have both types of carbons. Okay. Now, of course, when this is combustive carbon, especially in that case, you will have impurities. Impurities, primarily hydrogen. Also, in the case of pyrolytic carbon, sometimes you will have some hydrogen impurity as well, and which you need to remove at a later stage. Okay. Now, there was one experiment which was done long time back. So I have taken it from this book. This reference is here from 1965. Chemistry and Physics of Carbon, Volume 1. So I read about this experiment where this was one of the very initial experiments before even the today's version of CVD, where carbon was produced in the premixed flames and diffusion flames. So what is, again, in case you don't know, what is a premixed flame? Where you have a fuel, let's say any petroleum product or any gas which is flammable. So you have one fuel and one oxidizer. So it contains oxygen, let's say air, and they are mixed before being subjected to a flame. Okay, and what is a diffusion flame? Diffusion flame is where fuel or whatever fuel plus inert gas, there is no oxidizer. So that is the whole point. The oxidizer is not supplied from outside, but it may come from the ambience. Okay, so these are the two types of flames, and the experiment that was performed was, it looked something like this. There is a burner, and then on top of that, you just have a chamber where you have either a premixed flame or a diffusion flame, but in both cases you have an organic fuel. And what you will get is, you will get these smoky particles. Now you will say that, yeah, I also can get these kind of particles from the candle. Yes, but if this is done in a very controlled way, and the particles are collected and their concentration is understood. Okay, and then you can also try to make a circuit out of it. Okay, why do you do that? Because you also want to collect the particles. In order to collect the particles, there should be some sort of attractive force. Okay, so then you make a proper collector, and that is how you collect your carbon particles. Now you try to optimize this process. As I said, so this setup is for optimizing the process. And what are the parameters? Then you will optimize. You can try out different collectors. That is how we have come to the modern day, the optimum collectors for graphene and carbon nanotubes, because these kind of experiments were performed where a lot of different catalytic surfaces were tried out. Now, of course, when you have the premixed flame, then you will change the ratio of the gases. So your whatever is your fuel, that is your that is the source of your pyrolytic deposition. So you will change the ratio of that. You can also change the ratio of the carrier gas. You will change the temperature. You will change then you will optimize also what you achieve. So optimization means you will always, every time you change the process parameter, then you will see what kind of carbon do I get. Now what is the crystallinity of that kind of carbon, and what is the porosity of that film, and how long do I need to perform this experiment, and at what temperature I need to perform that experiment. So this electric circuitry that you see, that is also used for heating the substrate. The joule heat, just by joule heating, right? So you can also see then what kind of temperatures you need, and so on. And this was the optimization that went on for developing the CVD and for developing the optimum pyrolysis condition for gaseous hydrocarbons. Okay, now in this kind of experiment, there were 4 types of pyrolytic carbons. They were they had different crystallinities. I have not given the details of all 4 types, but the thin films that were deposited at 1200 degrees, that were, that had the largest crystallites. So this again is, this kind of characterization is done by X-ray diffraction techniques that we will learn in the characterization techniques. X-ray diffraction will basically tell you what is the value of LA and what is the value of LC. You can back calculate from there. So by that, by characterizing the material, this type of film was found the best quality film with the largest crystallites. Now these kind of the materials, at that time they were not called graphene, they were rather called either pyrolytic carbon and in some case pyrographite, when the material was more closer to graphite and when it had reasonably large crystallites, then they were called pyrographite in the past. And the one that we now call graphene, as I have mentioned multiple times, that was just called single layer graphite because it is the single layer of graphite. So now we come to the method of making graphite from this pyrolytic carbon or pyrographite. So pyrolytic carbon, if it has a very poor density and poor crystallinity, you will just call it pyrolytic carbon. But if it has a reasonable LaLC value, then you will call it pyrographite. Okay. Now, how do you make industrial pyrolytic carbon or industrial pyrolytic graphite from this material? Okay, so number one, you will choose the carbon films with high density and larger LaLC. Why high density? Now, high density may not be a requirement for some of the graphene related applications nowadays, but now here we want to make graphite. So whenever we want to make graphite, we need to have a less porosity, high density of your film. Okay, and now this, what can you do? As I mentioned, you can provide it certain heat in order to get into a more stable form, in order for the defects to anneal out. What are the defects? Non-6-membered rings. So, and also the organization. So what you do is you perform a heat treatment of this kind of pyrographite, and then what you get is known as pyrolytic graphite. Okay. Now, how do you perform the heat treatment? Well, for a film, the best option is to do it by hot pressing, because that also provides certain pressure to your film. So when you provide certain pressure, of course, you will get flatter films, and at the same time, you are also providing it sufficient heat, so it gets organized, organized in ABABA fashion. So hot pressing of this kind of pyrolytic graphite films is what is done for getting the industrial scale pyrolytic graphite. Okay, now this pyrolytic graphite material, after the organization of your crystallites, when it has less than 1 degrees of what is known as Mosaic spread, then it is known as highly oriented pyrolytic graphite, or HOPG, which is a very common material in the case of HOPG is what you can actually buy, and then you will use it for a large number of graphite related applications. So what is this Mosaic spread? First of all, okay, so you see, this is a polycrystalline graphite material, right? You will get smaller crystallites. They will organize, but they will not be organized in a global way. They will be organized locally. Okay, so local organization, you will call it, it's like a polycrystalline material. So here I have shown, say, 3 crystals. One is like this, the other one is slightly tilted, the other one is like that. So it is a polycrystalline material. Now that angle, if you draw a line on the surface, and then there is this angle where you have certain crystallites which are not completely parallel, exactly parallel, that angle, and the average of this angle throughout your surface, that is known as the Mosaic spread angle. So this angle needs to be less than 1%. You can imagine 1% is so small. And interestingly, you can get graphites, samples which are up to a couple of centimeters long. In this way. So it is polycrystalline type of graphite, but it is still the angle is the Mosaic spread is less than 1 degrees. So that is what you call highly oriented pyrolytic graphites. You have these tile-like structures. Okay. Now this is a picture of the sample. This is from my lab. This is how you see. This is a 1 centimeter by 1 centimeter. HOPG substrate, HOPG material that we purchased. So this is how it looks like. You can see that this is a very nice and shiny and with very high purity, and this particular the sample had 0.4 degrees of Mosaic spread. Okay, now it is a polycrystal, and the single layers of this. So now we know that where did we start? We started from what is actually known as graphite, CVD deposited graphite, graphene, and then we converted this graphene by heat treatment into graphite crystal. Now what people also do is they remove one layer of this HOPG crystal to get a single layer of graphene. So single layer of graphene was otherwise very difficult from the CVD, the raw material. There it's more difficult. Of course, there are methods. We'll talk about them that you can you can also get single layer or bilayer graphene from there, but much easier method is to just purchase an HOPG sample and then by a tape or some other exfoliation methods, you can remove single layers of graphene from there. What is exfoliation? Means removing something, peeling something off. That is known as exfoliation. So this is one of the most common applications of HOPG nowadays, that it is used for exfoliation and for giving you graphene. Okay, but other applications, the actual industrial applications of HOPG, very much used in X-ray optics. So because I told you, or I didn't tell you, I don't know, that the graphite is transparent to X-rays. So now you can make a lot of diagnostic tools or little parts of your spectrometers, X-ray spectrometers, that you can use. But there you need good quality graphite, and high purity and very small mosaic angle. So HOPG is used a lot in X-ray optics. You also use it for making ion beam detectors, and of course various kinds of electrodes and conductive supports. So you can see that this is the mica-like material layered structure. And of course, this is also an interesting test sample for various instruments. So you have a lot of characterization instruments where you, for example, when you want to calibrate your instrument, for example, for the angular spread, then you can use HOPG, because these samples have very small angles. So if you want to make something very flat, you want to calibrate your certain parameters of your instrument, then you can also use HOPG, which is actually very frequently used for as a test sample. Okay. Now, in general, HOPG is a very high quality graphite. So you can get these very nicely flat structures of relatively large sizes, which is otherwise difficult with other types of natural graphite. Also, it is not it's extremely difficult to get these kind of samples, and that is why this is one of the most sophisticated carbon materials, you should say, HOPG. Okay, so this is also reasonably expensive, but this is one of the most important industrial carbon materials, industrial graphites. I need to also mention that there are some other methods where you can get graphite, which is it is known as catalytic graphitization. So when you're collecting your these graphene sheets during CVD, that's also that has a catalytic support, right? So metal catalysts are always helping the growth of carbon materials, or providing an orientation to the carbon materials. Okay. Now, in this case, what you can also do when you're making large scale graphite, so you're not making a certain type of sample, but you're making bulk graphite. In that case, what you can do is, when you're carbonizing a polymer or carbonizing any organic material, which maybe even mesophase pitch, for example. So whenever you're carbonizing it, what you can do is you can already add some metal nanoparticles into it. Or not nanoparticles, but even slightly larger particles, but you can add the powders of metals onto it. And what happens is, on the surface of these metal particles, not just surface, but the area surrounding that surface, you have what is known as a carbide, metal carbide forming. So if it is iron, then you have iron carbide forming around that surface. And then this carbide further precipitates into graphite. And then afterwards, after you have done the heat treatment and you have now your bulk graphite material, in that case, then you will leach out the material. So you will get the metal. So you will get rid of your catalyst afterwards. So this is one more method by metal carbides as well as silicon carbides can precipitate graphite. So we will not go into the details of this specific method, but these are all the methods of graphite preparation.